All right, today we're going to look at section 7.2, some trig integrals. This is different than trig substitutions. They are different things. When I say trig integrals, I mean looking at integrals of the form cosine squared x sine cubed x dx, or sine x cosine to the fifth x, or different variations of sines and cosines, and later we'll look at some which aren't just sines and cosines, maybe have some tangents or cosecants or other versions of trig functions. Let's actually start with this one that's at the bottom. It's something we've seen something similar to this already. So sine x cosine to the fifth x. We've actually already seen an example of how to solve this. So when we have a sine, a single sine, and everything else is a cosine, we can actually use a u substitution with u equal cosine x. So the du is negative sine x dx, which we see up here without the negative, so we put a negative in and take the negative out, and the integral becomes negative sine x dx is du, cosine to the fifth is u to the fifth du. So that's minus u to the 6 over 6 plus c, which is negative cosine 6x over 6 plus c. And so a similar argument will work if we have a single cosine and the rest are sines. We also saw an example which is a bit more complicated, but uses the same idea. Cosine cubed x, sine cubed x. So for this example, we can actually save one of those signs. Write it as sine squared x, sine x dx. The sine squared we can write as 1 minus cosine squared. And now we have a single sine and everything else is cosine. And in that situation, we can let u equal cosine and solve the problem. So we see sine x dx, we need minus sine x dx, so we make a negative and we make a negative, as always. So negative integral, u is cosine, cosine cubed is u cubed, 1 minus cosine squared is 1 minus u squared, negative sine x dx is du. We can push the u cubed through, and then integrate each piece. And finally return it to cosine. And that's our answer. For some more complicated trig integrals, we have to keep in mind these half-angle formulas, which you may have seen at some point way long ago in a trig class. But these formulas are true. I'm not going to prove them. But they are true. Both of these formulas are true. They allow us to turn a sine squared into just a cosine. Not cosine squared or anything. We've reduced the power, which is great. Right? It really makes things a lot easier in a lot of situations. So we can change sine squared or we can change cosine squared using this half-angle formula. So So for instance, if I said just integrate sine squared x dx by itself, well, we can notice that that's the integral of 1 minus cosine 2x. That's our half-angle formula. That's 1/2 minus cosine 2x over 2. 1/2 integrates to 1/2 x. If I just had cosine 2x, the antiderivative would be sine 2x divided by 2. So I need a sine 2x divided by 2 for integrating cosine 2x, and then I still have that extra 2 in the denominator. And it's still a minus because the derivative of sine is cosine already. So the final answer is 1/2 x minus sine 2x over 4 plus c. So how about integrating sine squared cosine squared? There's no way to get just a single sine. If this were sine cubed, then I could save one of the sines, turn the sine squared into 1 minus cosine squared, and then apply a u substitution. But because these are both even powers, there's no way to save just one of them and turn everything into the other version. And so in that case, we actually need to apply our half-angle formulas. Sine squared is 1 minus cosine 2x over 2. Cosine squared is 1 plus cosine 2x over 2. But now we can multiply everything out. And if we just look at the numerators and we FOIL, I get 1, I get minus cosine 2x, I get plus cosine 2x, and then I get minus cosine squared 2x, all over 2, all over 4. Well, the minus cosine 2x and the plus cosine 2x cancels, and this becomes 1/4 minus cosine squared 2x over 4. Well, that's 1/4 x minus 1/4 integral cosine squared x dx. And so we've managed to simplify our integral from sine squared cosine squared down to just finding the antiderivative of cosine squared. But that's exactly analogous to finding the antiderivative of sine squared, which we did just a minute ago. We're going to use our half-angle formula. A half-angle formula for cosine squared is 1 plus cosine 2x over 2, rather than 1 minus. So if I can actually bring this 2 out, it makes 1/8 integral 1 plus cosine 2x. One integrates to x. Cosine 2x integrates to sine 2x divided by 2. And so 1/4 x minus 1/8 x minus 1/16 sine 2x. And that's the answer. So just a quick summary, and then that's really all we need to say at this point about this section. Summary. If we're looking at sine to the k x cosine to the m x dx, if they're both k and m are even, we use the half-angle formulas. if one is even and one is odd, well, if one is odd, that's really all it takes. If one is odd, say sine to the fifth, then we can save one of the signs and use 1 minus cosine squared for the other signs, and then use a u substitution. Right? Save 1, use sine squared equals 1 minus cosine squared, or cosine squared equals 1 minus sine squared, and then the u substitution. All right, so that's all we need to say about this section. See you next time.